Alright, let us now focus on constructing proofs, predicate logic. That is section 9.3. It'll take time before you get to do this with facility, but let me just give you an idea of how this is done. We will begin by constructing proofs for universal statements and then proceed to the notion of, or the possibility of, constructing proofs for particular statements. Constructing proofs for universal statements is a move called universal instantiation. Universal instantiation, in other words, you are instantiating from a universal statement to a particular statement. So this is how you do it. Let's assume that you have a statement like this. All humans are mortal. Socrates is human too. Therefore, or so, Socrates is mortal. This is how you do it. You symbolize this. For all x, if x is human, then x is mortal. For all x, if x is human, then x is mortal. That's step one. Symbolize this. Socrates is human. Notice that this is already an instantiated statement. So you will have like that. They switch places. Socrates is human. You have this going on. Human there. Socrates is human, and that's what I brought there. Therefore, Socrates is mortal. Again, you just do that operation like that. So you have MS. Here's what you do. Universal instantiation. You can't do modus ponens with this. Everything has got to be uniform in order for you to do modus ponens. So for example, you cannot say, aha, here's HX and here's HX. I can do modus ponens and drop the MX down here. No, you can't do that. What you will need to do is to drop this X by a process called universal instantiation, okay, and replace every instance of X with S. First of all, you drop the X and you replace every instance of X with S. So this is what you do. HS MX, say 1 universal instantiation. Okay? Now you can do modus ponens. Pardon me, that is wrong. Now you can do modus ponens. When you do modus ponens between 2 and 3, that's what you get. MS. 2, 3 modus ponens. This is called universal instantiation. Instantiation, like that. You can instantiate to any letter you wish, provided it allows you, let me correct that. You can universally instantiate to any letter you wish, provided it allows you to uniformly distribute the constant, the individual constants, in a way that permits you to do modus ponens, disjunctive syllogism, or to apply all those 18 other rules of inference. That's called universal instantiation. Now, if you look at page 446 and 447, you get a demonstration of universal instantiation. Oh, look at that. I used the example that they use in that category. Now, some things have got to be said about universal instantiation. Let's assume that instead of having this kind of formulation, this is what you have. Hx, sorry, that's wrong. Let me correct that. Instead of having that, this is what you have. For all x, you have hx my. If you are to do universal instantiation on this, the only letter that will be affected here is the x, not the y. In other words, we are saying that this x here binds that x, but this x does not bind that y. So you only instantiate letters that have been bound by the quantifier. Let me put that down. Instantiate only the letters bound by the quantifier. So if I were to instantiate this, it would be H, S, M, Y. That one remains untouched. It remains untouched. Always make sure you instantiate all the letters that have been bound. So X here is bound by that. Now suppose I had something like JX. Again, notice this X binds that X, but this X does not bind that J. Why? Because X, the scope of X, is limited only to what it has been set against. The scope of X does not cover this JX here. It doesn't. So the next rule is instantiate only the letters within the scope, of the quantifier. So if you look at all those examples, look at page 446. At the very bottom of 446, if you have your book. Look at example A. For all y, ac.by. Notice that y binds the y against b, but it doesn't bind the c, because c, after all, is an individual constant. And then look at example B. For all y, ac.by, and then you have ac.bd. Notice that it is also a universal instantiation, and the person has instantiated to a different letter. Both instances of universal instantiations are correct. You can instantiate to the same letter. You can instantiate universally to a different letter. C is also universal instantiation, and notice that it has two quantifiers. It has the existential quantifier as well as the universal quantifier. And the universal quantifier in C has been dropped in step 2. And notice that the X in premise 1 against G has been replaced by an A in premise 2 or step 2 against G. The Z has been left untouched because E has not, the backward looking E has not been dropped. And then you have D. The problem with D is you have replaced a variable with another variable so that the first variable has not been instanced by the second one. So you always instantiate to a constant. Do your best to instantiate to a constant. And then you have E. It is not a uniform replacement of Y. You have A, C, and B, D. If you replace Y with C, you must replace all occurrences of Y with C. If you choose to replace it with D, replace all occurrences of Y with D. And then the final important one here is try your universal instantiation, or yes, do universal instantiation on a whole line, not on a part of a line. For example, suppose I had something like this. Suppose I had, for all x, hx mx dot jx. I cannot do universal instantiation on this until I first of all break it off from the jx through simplification. So I need to have that hx arrow mx and then say one simplification, and then after that then I can do universal instantiation and say hs arrow ms. Okay, that's how it works. So that's called universal instantiation. Let's move on to existential instantiation in the next section, in the next lecture.